this presentation, we introduce the fast Spatio-Temporal Transformer Network, a deep network for video painting. In computer vision, inpaint is the process or technique of restoring a missing or damaged part of an image, or removing an object or watermark from an image. The inpainting process applied to videos is currently a big challenge, because additional information must be extracted from neighboring frames, which elevates significantly the computational cost of the inpainting process. Recent video painting works rely on the use of the transformer architecture. Despite all of them achieving state-of-the-art results, we could only find these three works in the literature: the STN, the DSTT, and the fuse former. The transformer is a neural network consisting of attention mechanisms. It has been used in several works achieving state-of-the-art in many different areas of deep learning. In an attention mechanism, representations of the network's input are calculated, the Curie, key, and value matrices. This formula summarizes the attention process, where we perform the softmax of the normalized multiplication of the Curie and the transposed key matrices, and then we multiply the obtained score with the value matrix. In practice, the attention calculates the relevance a single piece of information has with all other pieces. However, the transformer has two major problems. The first is that the complexity of the transformer is quadratic, and the second problem is that the layer's activations occupy too much memory. These activations are the inputs and outputs of each attention layer that are stored on the memory and that are used during backpropagation for gradient computation. The STN, mentioned before, is the first to explore the transformer architecture to tackle video painting applications, because it inherits the transformer's problems and also extracts information from multiple frames of a video. Its use requires sophisticated equipment. To solve these problems, we propose the fast STN, that is a deep network for video painting. It is heavily based on the STN, but solves its high memory consumption problem by implementing the reversible layers method into the transformers blocks of the network. This strategy allows for a reduction in memory usage by up to 7 times, and a 2.2 times faster execution time approximately. The reversible layers is a method that eliminates the need to store the layer's activation in memory. In this method, the activations are deleted from memory and are retrieved on demand during backpropagation. This is the overall architecture of the fast STN. Similar to the STN, T-frames and binary masks enter the network going through an encoder, 8 transformer blocks, and a decoder. The reversible layers method is applied directly to the transformers blocks. With a GPU with 16 GB of memory, this table shows the memory consumption in FPS at the inference of the STN and the fast STN models. A sequence of not more than 13 frames could fit in the GPU with the STN, while with the fast STN, a total of 123 frames could fit in the GPU. This table shows the quantitative evaluation of both models, in function of the metrics PSNR, SSIM, and EWARP. As you can see, all methods present similar results in terms of accuracy. This is a qualitative comparison of both models. The first row shows frame samples from frame sequences that went through the models. The second row shows the respective masks of the frames of the first row. The third row shows the inpainted frames by the fast STN. The fourth row shows the inpainted frames by the STN. We propose in this work the fast STN, a state-of-the-art video painting network that has in its core transformer blocks that were modified in order to reduce its memory and time consumption of execution. We conclude that there is no quality loss in exchange for reducing memory consumption and increased speed. Thank you.